This is part 4 of Microchip's cryptography primer. In this part, we'll talk about asymmetric cryptography. Public key cryptography, also known as asymmetric or public-private key cryptography. Also, you may have heard the term PKI, which stands for public key infrastructure. That is also a term often used. Consider that PKI uses two mathematically related keys rather than the same key on both sides. If you can imagine that same lockbox with two mathematically related keys, the first key could lock it, but you would need to use the second key to unlock it. The first key would not be able to both lock it and unlock it. They need to work together. Key distribution becomes very easy. One key can be shared publicly, and it's called the public key. The other key is held very privately, and it's called the private key. The security and privacy of this private key is critical to the security of your system. In the public key infrastructure, or PKI, every element has its own key pair. Key pairs should never be shared. So if you make two different devices, they should have two different key pairs. The basis for security is the unique identity of each element. So you don't want to have two different devices sharing that same identity. Let's examine how that public key is exchanged between Alice and Bob. Again, this is the simplest form of key exchange where Alice and Bob know and trust each other. Bob can give Alice his public key, and Alice is assured it's genuine and trusted based on her knowledge and trust of Bob. There is no reason for Bob to give Alice an erroneous key, and there is no reason for Alice to question the key. Alice can provide Bob her public key in the same way. Again, they know and trust each other. Unlike the symmetric key exchange that we talked about before, this does not have to happen in a relatively secure environment. The public key is not a secret. You could write it on the side of your car if you wanted to. It's simply not a secret. It's public information. Let's look at an example of asymmetric authentication. Alice wants to authenticate she is connected to Bob. Alice and Bob know and trust each other and have their own public-private key pairs. Alice starts off with a random challenge which she sends to Bob. Bob then digitally signs it with his private key and sends a digital signature to Alice. Alice, armed with Bob's public key, can use that along with the random challenge she initially sent to Bob to verify that digital signature. What exactly is a digital signature? It is not an encrypted return of the challenge. Digitally signing is a complex mathematical function which takes the private key, the random challenge, and a new, unique random number to create the result. The resulting digital signature can only be verified using the signer's public key. A verify is not a decryption. A verify is another complex mathematical function whose only goal is to determine if the sender's private key was used in creating that digital signature. The result of the verification is a yes-no result. So more accurately, a signing actually looks like this. This is what I originally showed you, but this is what actually happens. A nonce is short for number used once, is injected into the signing math when Bob signs that challenge. What this does is it makes each signing unique, and it thwarts what's known as a plain text attack. A plain text attack is an attempt to calculate secrets from output produced from known input. If you can imagine an adversary poses as Alice and Bob believes them, and the adversary sends them challenge after challenge after challenge, and then Bob signs them and sends back the digital signature. The adversary would be able to calculate what Bob's private key is. But by injecting randomness, this defeats that attack. Even if the same exact challenge is signed, a completely different yet verifiable signature is calculated. So think of this. Imagine Alice, for reasons beyond comprehension, decides to send the same challenge to Bob over and over and over again. And Bob signs each one. Each time he signs it, he will create a completely different digital signature, yet every one of those digital signatures will be able to be verified using Bob's public key. And by the way, whenever we do this sort of authentication, That random challenge always needs to be different. You should never use the same random number. Asymmetric message authentication. The previous slide talked about identity authentication. Now we'll talk about how we authenticate a message. Alice generates a message. She then hashes that message and then signs the digest with her private key. This creates a digital signature. She sends both the message and the digital signature to Bob. Bob takes the message, saves it on the side. He doesn't know if it's genuine yet. He doesn't want to use it. He takes the message, hashes it, uses the resulting digest along with knowledge of Alice's public key to verify the digital signature. And now he knows the message came from Alice, nobody else but Alice, and also the content was not modified in any way. Thanks for watching Microchip Channels, and I hope you learned more about embedded security.